Okay, so free body diagrams give us a picture model of what is happening in these systems. We have to draw them in terms of vectors, which means in an arrow, and we draw them in the direction of the force. Okay, you'll see that in this particular free body diagram, we've got a hand, right, that's applying a rightward force on this book. Okay, it's pushing it to the right. In this diagram, we don't see any friction taken into account here. So this is a frictionless surface, which happens more often than not in high school physics, right? So we're looking at perfect world here. Sometimes we use friction, sometimes we don't. But in this case, since we have nothing opposing the motion, that means we have no frictional force here. Since our object is not accelerating in the vertical direction, what does that mean about these two forces? What do you think? They're equal to each other, right? Our book is not moving in the vertical direction at all. So that means the normal force here, or the force of the table on the book, which we would just relabel as the normal force. The Earth's mass, okay, yeah, we just called the force due to gravity. Those two would be equal to each other, right? Since there's no acceleration in the vertical direction, we see that it's equal. If we only have one horizontal force, what does that mean about our horizontal acceleration? Which direction is it going? Positive or to the right? Okay, there's nothing opposing our motion. That means we have some acceleration in the horizontal direction. Okay? What do we know about something that moves at constant velocity? What do we know about the net force of something that moves at constant velocity? Did we talk about that last time? It's zero, right? So let's look at our net force equation. F net is equal to mass times acceleration. If I'm moving at constant velocity, that means my acceleration is equal to 0. Okay, so mass times 0 would always give us a net force equal to 0. Okay? So since my object is at rest, or what else is it called if we have equal forces? Equilibrium, right? If I'm at equilibrium, my net force is also 0. That means my upward equal my downward, or my rightward equal my leftward. Okay, are we on the same page from that stuff so far? When we draw free body diagrams, it's important that you have to label each and every force. Is it a tension force, which we talked about being labeled F sub T is a tension force. That's when something is hanging. This is the what force? F sub capital N. What would that be? The normal. F sub G is equal to gravitational. Okay, and what if I say FAPP? What would that maybe stand for? Do you know? Applied, right? An applied force. Okay, you could also say F sub push for a pushing force or a pull or whatever you want to put, that's fine. Usually I just say APP for an applied force. Okay. Right now, what do you think this one might stand for? F sub little f, what do we think? Not a bad guess. This one is for friction. Okay, so this is applied, and this is a frictional force. And what do we know about friction? Does it always go in the negative direction? No, friction always opposes the motion. So if I am applying the force this way, my friction would oppose the motion in the other direction. So here would be my F applied, here would be my frictional force. Okay, it always opposes the motion. Something that we need to pay attention to on our free body diagrams is that our vectors always start from the system and go outward. Okay, we would never see a force that looks like this. Even though we're pushing our book to the right, it wouldn't look like that, right? We don't go into the center of our diagram. We always go out from the center of our diagram. Okay, so here's our system. We have a rightward force, which means we need to start at our system and go to the right. Okay, we don't ever put our arrows into the system. Okay. Force vectors should be drawn to scale. That means if two forces you know are equal to each other, you need to draw them equal to each other. If one force is substantially bigger than the other, that means you need to draw it substantially bigger than the other. Okay, we're not talking about getting out your ruler and measuring into scale like that. I mean in a general scale. So give them a proportion. Okay. Force arrow should always be pointing away from the object. Okay, so I just made a note about that, but that's really important. When we're dealing with forces, we use the same kind of coordinate system as we do when we were dealing with projectiles, right? We can never mix horizontal and vertical forces. Okay, next class we're going to get into forces in 2 dimensions, but it's important for you to understand here that you can't compare the normal force to the applied force because they're in 2 different dimensions. We cannot mix x and y, just like we couldn't mix it in the projectiles section. Okay, we have to take into account vertical forces and horizontal forces as separate identities. Okay? All right, let's look at some practice here for free body diagrams. Okay, draw the free body diagram of a box accelerating in the rightward direction. And it tells us to include a frictional force. So here's my system. It always starts with the dot, right? Or you can draw a pretty picture for it. I don't do that, okay? Usually your system is just labeled as a dot. So let's talk about what has to be moving the box, right? If we're accelerating in the rightward direction, what type of force has to be being used to get that box to be moving to the right? A contact force of some kind, right? So I'm just going to write that as F applied, okay? And if it's accelerating in the rightward direction, is the applied force greater than, equal to, or less than the frictional force? The applied force is greater than. So we don't know necessarily the scale, but we know that our applied force needs to be greater than our frictional force. If they were equal to each other, we would be moving at constant velocity. Okay? Or we would be moving, or we wouldn't be moving at all, right? We wouldn't have any acceleration. So there's a couple different situations we could be looking at there. Does our object have any vertical forces? Yeah, it still does, right? Gravity always acts. So we're going to say F sub g here. And is this box floating in the air and we're pushing it? Probably not. It's probably resting on a surface, even though it doesn't say that explicitly. So we call that the normal force. What do we know about the normal force and the gravitational force here? They're equal to each other. Okay, isn't that how you indicate that 2 lines are equal to each other? Okay, there we go. All right, I know my math a little bit. Okay, so it's not telling us that it's accelerating in the vertical direction. So it doesn't really matter that we draw these to scale in comparison to the rightward and leftward forces, as long as those 2 are equal to each other. Okay. So if we wrote our net force equation here for the horizontal direction, so F net in the horizontal direction, I'll just put a little X there to tell us it's horizontal. What would be my net force equation here for my horizontal forces? Yeah, very good. F applied minus the frictional force. Okay, because it's rightward or positive forces minus leftward. Okay, are we on the same page so far there? And it tells us we are accelerating. So if we were going to solve this problem, we'd substitute MA equals F applied minus frictional force. Okay? If we were going to start solving for that, start breaking it down, you need to see that there's always a substitution available for that net force. Okay, which is mass times acceleration. Okay, so what happens in your vehicle when you coast? What are you doing? Yeah, are you applying the accelerator? No, so is there any applied force here? No. Yet our car is moving in the leftward direction. What direction does that mean friction has to be going? The rightward direction. So we have a frictional force here that is slowing our vehicle down. Okay, what other forces do we have acting here? Good. F of G and the normal force, right? The car has to be on a surface, right? It's got to be on the road, which means that that road or the earth is applying an upward force as well. Okay, so if we were going to set up our net force equation here again in the x direction, do we have any positive forces? Right, you could say your friction force is positive because it's going in the positive direction, but our car is also going left. Okay, so you can configure it either way that you want to, and it doesn't make a difference. You can make left the positive direction here, since that's where our motion is going. That's totally up to you. Okay, but if we're doing rightward minus leftward, we would do friction force minus 0. Okay, and that's just saying that the rightward direction is still positive. Okay. Questions here? Okay, so make sure that you're reading what the situation is calling for, because coasting should tell you there's no applied force, right? We're not even applying the brake. We're just applying, or we're just letting friction do the work. Okay, the last little section for this portion that I want to talk about is something called terminal velocity. What's the word terminal mean? Final, right? The end. Okay, final. So terminal velocity is a constant velocity that is reached when the drag force equals the force due to gravity. Okay. And drag force is another word for air resistance. So what direction do you think the drag force normally goes? Right? As something is falling through the air, gravity is pulling it down, and air resistance is slowing it down, right? It's pushing back up. So that means the drag force or the air resistance force will usually be going in the upward direction. Okay? Okay, so let's think about this question. What reaches terminal velocity faster or sooner? Okay, a heavy compact object or a light object with a large surface area? What do we think? A light object, right? So that means the drag force or the air resistance force is going to impact that light object with a lot of surface area, like a piece of paper floating, right? It's going to stop accelerating sooner than a heavy object that's really compact would. Okay? So that piece of paper that's floating is going to fall and it's going to be accelerating, but soon enough that drag force or the air resistance force is going to catch up with it, and it's just going to fall at a constant rate. It's not going to accelerate anymore. Okay? Whereas a compact object is going to keep falling and keep speeding up and eventually reach its terminal velocity, but it might not even reach it before it hits the ground. Okay? We're going to watch a little video on terminal velocity because some other people can explain it better than I can, I think. On Google Classroom, I put up a link to an Ed Puzzle, which is a video that you watch and you interact with while you're watching it. Okay? So I want you to pull up that link.